2025 could be an explosive year for researchers at Oregon State University. They are predicting an undersea volcano called Axial Seamount will erupt sometime this year. What if I told you that something is stirring in the darkest, coldest depths of the Pacific Ocean? A volcanic monster long thought to slumber, now pulsing with pressure and heat beneath the seafloor. For years, the Axial Seamount, an enormous undersea volcano located 300 m of the Oregon coast, was considered predictable, almost tame by geological standards. It erupted on a schedule every 13 years or so and then settled into silence. But in early 2025, something changed. Tectonic pressures are rising. The seafloor is bulging. Magma chambers are inflating at an alarming rate, and seismic signals coming from beneath the Pacific are beginning to look unfamiliar. Could this be the beginning of something far bigger than we've seen before? Or are we witnessing the early warnings of a catastrophic undersea eruption, one capable of shaking the Pacific Northwest from beneath? Let's dive into 5 shocking new discoveries about Axial Seamount and why experts are beginning to worry that this underwater giant is waking up in ways we've never seen before. The seafloor is rising fast. It started with a subtle uplift, just a few millimeters at first, but by March 2025, no AAA researchers were recording vertical movements of nearly 20 centimeters across the summit of Axial Seamount. And it's not slowing down. This kind of inflation is a telltale sign that magma is moving upward, pressurizing the crust from below. But what's truly alarming is the rate. This uplift is happening twice as fast as it did prior to the 2015 eruption. Using high-precision bottom pressure recorders and satellite GPS arrays anchored to the seafloor, scientists confirmed that the central caldera is expanding outward like a balloon. Why does that matter? Because if the crust above the magma chamber can no longer take the pressure, it will fracture violently. And when that happens, it won't be a slow trickle of lava. It will be an explosive release capable of triggering hydrothermal vent collapse, deep-sea tsunamis, and even distant seismic activity. The last time this volcano erupted, it was considered minor. But this time, the warning signs are multiplying. Adding to the urgency, new data suggests the inflation may be occurring unevenly. One side of the summit is lifting faster than the other, indicating asymmetric magma intrusion. This kind of uneven stress can cause tilted fault lines to form, increasing the risk of sudden rupture. Furthermore, thermal imaging from remotely operated vehicles has shown cracks in the surrounding basalt glowing faintly with residual heat, a sign that magma is now only a few hundred meters below the seafloor. And in certain areas, faint sulfur plumes have been observed, indicating minor degassing has already begun. Scientists are particularly concerned about the potential domino effects. As pressure builds beneath the summit, adjacent volcanic ridges and fractures, many of which haven't been mapped in detail, could reactivate, creating a cascade of underwater volcanic activity. Axial Seamount is also closely connected to the Juan Fuca tectonic plate, which slides slowly beneath the North American plate in one of the most dangerous subduction zones on Earth. If seismic energy from a major axial eruption transfers into that fault line, it could destabilize the already fragile boundary, raising the nightmare scenario of triggering a massive earthquake or tsunami along the Pacific Northwest coast. In short, this isn't just about a single volcano anymore. The entire region is part of an interconnected geological system, and axial sudden awakening may be the first domino to fall. A new type of tremor, and it's spreading. In January 2025, underwater seismometers picked up something strange. Low-frequency earthquakes rolling beneath the seafloor. But these weren't the normal rumbles of tectonic plates. They pulsed like drum beats. Some lasted for hours. Others seemed to migrate outward like a wave radiating from a central point. Geologists call this a seismic swarm, but this one is different. The tremors are deeper, more harmonic, and in some cases nearly identical to signals observed prior to eruptions at Kauai in Hawaii and Batabanga in Iceland. The most likely explanation, magma is rising through narrow conduits, cracking surrounding rock in rhythmic bursts. But here's the twist. Similar tremors have now been detected outside the axial caldera, suggesting that the volcanic system may be expanding. Recent analyses of tremor patterns have revealed something even more peculiar. Some of the quakes appear to follow a pattern of frequency modulation, increasing and decreasing in pitch, like a tuning fork under pressure. This has led to speculation that there may be alternating pulses of magma influx, surges that enter the chamber in waves, each one pushing outward and disturbing the surrounding crust. The migration of these tremors has also been mapped with extraordinary precision. What initially appeared to be a random swarm now shows clear directional flow, originating near the center of the caldera and propagating northwest. This directional migration has led scientists to propose that a new lateral dike may be forming, a horizontal intrusion of magma that could extend tens of kilometers beneath the seafloor. Supporting this theory are recent deep-sea sonar scans showing small recently formed cracks trailing away from the caldera. These cracks align almost perfectly with the tremor path and could represent weak zones that magma is exploiting. If a dike does breach the surface, it could trigger a chain reaction of vent openings across the seafloor. Even more concerning are the accompanying harmonic tremors, continuous low-frequency vibrations that last for minutes or even hours. These are typically associated with pressurized gas or magma moving in confined spaces, and are often a final precursor to eruption. Some of these harmonic signals have shown an eerie synchronization with rising CO2 levels in surrounding vent plumes, suggesting gases escaping in lockstep with the tremors. One geophysicist described it this way: "It's like the volcano is breathing, but every breath is deeper, stronger, and harder to ignore. And now it might be ready to speak." To add to the mystery, researchers have recorded ultra-low frequency signals, infrasound, using ocean-bottom hydrophones. These subaudible pulses are not well understood, but appear to correspond with the deepest parts of the tremor field. Some believe they may represent deep pressure releases from the lower crust or upper mantle, seismic size from Earth's hidden interior. Together, these discoveries paint a more complex picture of axial awakening. It's no longer just about vertical magma movement. This volcano is reaching outward, its influence spreading in all directions. And the signals, they're getting louder, more organized, and harder to dismiss. Superheated vents and signs of chemical superheated vents, and signs of chemical change. Axial seamount is home to hundreds of hydrothermal vents, deep-sea chimneys that spew mineral-rich fluids heated by volcanic rock. But in February 2025, researchers monitoring these vents made an unsettling discovery. Temperatures at several key vent fields had increased by 30 to 40 degrees Celsius in just a few months. That's not all. The chemical composition of the vent fluids had also changed. Normally, these waters are rich in sulfur and iron, but new samples showed elevated levels of helium-3, a rare isotope that leaks from deep within Earth's mantle. Helium-3 spikes are often a precursor to volcanic eruptions. Why? Because they suggest that fresh magma, not just recycled crust melt, is on the move. Meanwhile, deep-sea life near the vent is acting strangely. Giant tube worms and vent shrimp have begun migrating away from active fields, a behavior that's been observed before prior to hydrothermal collapse. Is it coincidence, or is the ecosystem sensing something we can't? To further investigate, scientists deployed autonomous submersibles equipped with mass spectrometers and thermal probes to continuously monitor the vent fields. These robots confirmed an abnormal rise in manganese and arsenic levels in the vent emissions, both indicators of aggressive rock dissolution caused by new magma contact. More concerning, the chemical fingerprint of the vent plumes has changed in a way that suggests the mixing zone between seawater and magma-heated fluids is shifting. This could indicate that magma is rising higher within the crust, decreasing the rock barrier between molten material and ocean. Some researchers are now modeling the possibility of a vent blowout, an explosive release of superheated fluid that could destabilize the surrounding seafloor. Similar events have been observed in other mid-ocean ridges where rapid magma ascent fractured the overlying rock and caused sudden vent collapses. Infrared imaging taken from submersible drones has also captured shimmering thermoclines, layers of varying temperature surrounding the most active vents. These anomalies appear to pulse rhythmically as though responding to pressure waves deep below. Some scientists speculate that these pulses may be tied to tidal forces interacting with magma chambers or the rhythmic cycling of gas release within the volcanic plumbing system. Curiously, trace amounts of rare gases like xenon and krypton have been detected, elements that are typically associated with deep mantle sources and rarely make it to the surface unless magma is rising unusually fast. This adds to the growing body of evidence that axial seamounts hydrothermal systems are being rewired by a rising column of deep earth material. If these signs are accurate, it may only be a matter of time before the seafloor structure around the vent becomes unstable. And if that happens, the resulting event may not be gradual, but sudden, violent, and potentially far-reaching. Seafloor cracks and fractures growing in seafloor cracks and fractures, growing in size and number. In March, a submersible drone survey captured new high-resolution images of fissures radiating outward from a volcano's central ridge. These weren't hairline cracks. Some were meters wide, others extended for kilometers. Long snaking ruptures through basalt and pillow lava. Even more troubling, some of these cracks are new, having formed just within the last few weeks. What's causing them? It could be tectonic stretching, or it could be something worse. Dike intrusion, where magma forces its way sideways through crust, prying the earth apart. If these dikes breach the surface, they can trigger explosive eruptions without warning, ejecting molten rock, gas, and ash directly into the ocean. Geologists are now using a combination of sonar mapping, LAR, and visual surveys to create a dynamic model of how these fractures are evolving over time. Preliminary simulations suggest that stress concentrations are building in a fan-shaped pattern radiating from the central caldera and focused particularly toward the northwest flank. This flank, composed of relatively younger lava flows, may be structurally weaker, increasing the risk of sudden flank collapse. Such collapses can lead to underwater landslides or slumps which displace enormous volumes of seawater. The result? Localized tsunamis, which, depending on direction and magnitude, could impact not only marine life, but also shipping routes in coastal towns across the Pacific Northwest. Even more alarming are the shallow gas pockets being detected beneath some of these fractures. Using sub-bottom profilers, researchers have identified trapped layers of methane and CO2 beneath the sediment. If a dike intersects one of these gas zones, the sudden release could amplify the explosiveness of the eruption dramatically, a phenomenon known as phreatomagmatic activity.